joint quality and business change event, but this is very much international event with two fantastic speakers from different parts of the world. We have Joe Kessler from Australia and Bruce Lynn from USA. At this stage, we're recording this, and the link, which will be up on YouTube for the recording, will be actually available at the end of this. And the slides will be available again, probably in about a week's time. At that stage, I would like to pass across to Brad to start the session. And thank you both very much for coming to talk to us today from different parts of the world.
Thank you, Margaret. We'll start the recording.
Thank you for taking the time to attend this presentation on two major misconceptions of systems thinking exposed. I'm Joseph Kasser.
And I'm Bruce Lerner.
Why you should watch this video. First of all, you should find out why I'm upside down. I'm upside down because I'm in Australia. Think about it. If you're having problems actually applying systems thinking, you're not alone.
We explain two of the misconceptions that are thwarting your use of systems thinking.
And if you stay to the end, you will find out how you can get a free gift that will help you understand both critical thinking as well as systems thinking and beyond.
The two misconceptions of systems thinking are: reductionism doesn't work, you need to use systems thinking instead.
And that open and closed systems are actually different types of systems.
So let me now give you an overview of what we're going to talk about. Misconception one is based on a misunderstanding of the words in isolation and how they're used. Reductionism and systems thinking are really analysis tools for understanding different types of situations. Both can suffer from blind spots. You haven't heard that before. In isolation actually has a place in the process of gaining an understanding.
And misconception two came about by people always bounding the same system of interest, but only dealing with one type of problem. The observer bounds the system of interest that they believe suit the problem. Always consider both the internal and external perspectives when assessing a problem.
And we'll explain what those are in a few minutes
as we go through the presentation.
After we've explained the two misconceptions, we're going to introduce the updated systems approach. It combines the best of reductionism and systems thinking, and it builds on the general systems theory to provide a methodology which minimizes blind spots and provides a universal systemic and systematic approach to identifying and remedying complex problems. We'll go through the first misconception, the second misconception, then we'll introduce the updated systems approach, share our conclusions and the lessons learned from this research, and tell you about the free gift. Misconception one, reductionism doesn't work. Many systems thinkers tend to dismiss reductionism because their perception is examining parts in isolation does not provide information about the system's behavior.
For example, here's a quotation. The behavior of a system cannot be known just by knowing the elements of which the system is made.
This is from Donella H. Meadows and Diana Wright, Thinking in Systems. This statement doesn't feel right. Reductionism does work in some situations. But first of all, let's take a look and see what reductionism is. I looked it up and I found this statement. Reductionism in philosophy, the view that asserts that entities of a given kind are identical to, or are collections or combinations of, entities of another, often simpler or more basic kind, or that expressions denoting such entities are definable in terms of expressions denoting other entities. Bruce, do you understand that? Because I don't.
Not really. I would have to go find a dictionary and take a look at those words and figure out what that meant in detail. And when I've done that before, I've often found that it turns into even more gobbledygook.
Anyhow, that quote from Britannica goes on, the idea is that physical bodies are collections of atoms, or that a given mental state, for example, one person's belief that snow is white is identical to a particular physical state. The firing of certain neurons in that person's brain are examples of reductionism. Reductionism defined in psychology. Reductionism is the belief that human behavior can be explained by breaking it down into smaller parts. Reductionists say that the best way to understand why we behave as we do is to look closely at the very simplest parts that make up our systems and use the simplest explanations to understand how they work. Reductionism is based on the scientific assumption of parsimony. That's Occam's razor. The simplest explanation should be used. But that really has nothing to do with in isolation. It's just an approach to gaining an understanding of something.
The term reductionism originated in 1925 to describe, in retrospect, the successful methodology that had been used in history up to and including the machine age to gain an understanding of what were then perceived as complex problems. It wasn't actually used for solving those problems. The meaning of reductionism has evolved since then in various ways. The term systems thinking was introduced in 1950 as a result of a paradigm shift in the concept of what a complex system is.
And if we look at Russ Ackoff's timeline, he talks about World War II marked the beginning of the end of what might be called the machine age, an age that began with the Renaissance. The dominant mode of thought in the machine age, according to Ackoff, looking back retroactively, was called analysis. And he says, like a child, man sought understanding by means of a three-step process, taking apart the things he wanted to understand, trying to understand how these parts worked, assembling his understanding of the parts into an understanding of the whole, and machine age man, who believed in the possibility of complete understanding, also believed it could be derived from understanding ultimate indivisible parts, and the doctrine based on these beliefs is called reductionism. Now, one source of the misconception comes from Ludwig von Bertalanffy in his Outline of General Systems Theory. He wrote, "In past centuries, science tried to explain phenomena by reducing them to an interplay of elementary units which could be investigated independently of each other. Independently of each other has been misinterpreted to mean understanding the parts in isolation. Anybody who builds a model understands that it's the first step in creating a model for understanding some types of situations. The variables in the system of interest are identified, such as the inputs or the subsystems of the containing or meta system, and then the effect of each variable on the whole in isolation is considered one at a time to create an equation showing the effect of that variable on the whole. And that means all the variables are held constant and only one is changed. The model is then developed from the resulting set of equations, and it applies to analyzing existing situations as well as creating conceptual models. Another source of the misconception is based on a misunderstanding of Ackoff's three-step process, taking apart the things to be understood and trying to understand how these parts work in isolation and assembling an understanding of the parts into an understanding of the whole. For example, here's a picture of a bicycle.
Anybody who wants to understand how the bicycle works does not lay the parts out at random. They lay them out so that they can see the relationships between the parts and they can understand how the parts work as well as the relationships between them.
And here's a more explicit form. And this is the form that was known in the 1960s as exploded diagrams. And according to the BBC, exploded diagrams are graphical communication techniques that show the relationships between parts by separating them as if there had been a small explosion along an axis. This innovation was a product of the Renaissance, so it didn't originate in the 1960s. And here's an example of an exploded diagram from one of the notebooks of Leonardo da Vinci. What about the Wright brothers? They used the lift equation to calculate the amount of lift that a wing would produce. When they use an equation, the equation contains the effect of each variable and the relationships between them. And what about the Savory steam pump 300 years ago? Or Roman aqueducts 2,000 years ago? Or Archimedes' lever even earlier? Could these have been conceptualized, developed, and built without an understanding of the parts and their relationships? Here's the missing link and why Ackoff was misquoted. Ackoff also wrote, an understanding of the whole can be achieved only if the relationships between the parts are understood. And this was found in the original paper, but not in the subsequent literature that cites the original paper, because this was on the next page or further down, and that's a key research finding. So if we correct the popular misconception, analysis is a three-step process, taking apart the things to be understood, trying to understand how these parts worked, so we remove the in isolation, assembling an understanding of the parts into an understanding of the whole. And here's a picture of a London bus from the 1960s. You can see that it shows the bus and it shows the internal parts. And that allows the readers of the Eagle comic in which this was produced to understand how the Routemaster bus works. So reductionism, it really is exactly this. When we assemble an understanding of the parts into an understanding of the whole, an understanding of the whole can be achieved only if the relationships between the parts are understood, as well as how the individual parts function. Properly performed reductionism provides an understanding of the system of interest.
So I've got a question. If reductionism was successful as a method for gaining an understanding of a situation, why did von Bertalanffy need to develop and use systems thinking for the same purpose?
Well, Bruce, the answer is it was a change in the perception of the nature of complex problems.
It was introduced by Ludwig von Bertalanffy, who was an Austrian scientist. He stated that concepts of reductionism in isolation were helpless in appreciating dynamics of organisms. Then he expanded the concept to all systems, so-called natural and man-made, and theorized systems as being open and closed. Russell Ackoff talked about systems thinking as another three-step process. A thing to be understood is conceptualized as a part of one or more larger wholes, not as a whole to be taken apart. An understanding of the larger containing system is sought, and the system to be understood is explained in terms of its role or function in the containing system.
So what about these problems, Joe? I have a really bad pain in my side. Or, look, David is falling down. Fred's PC is locked up. Or Lily's bicycle has a flat tire. Our cat does not want to eat anything. Or the bus will not start in the morning.
Let's pick up on that bus. It's a three-step process. The bus is a subsystem in at least two larger wholes or metasystems. The traffic system when it's on the roads, and the fleet of buses when it's in the depot, and that has maintenance facilities, administration, and so on. Well, we develop an understanding of the traffic and the fleet metasystem. And then the role of the bus in the traffic system includes providing transportation for passengers and providing traffic congestions at times.
On the other hand, the role of the bus in the fleet metasystem includes being maintained and repaired when breakdowns occur and being stored in garages. A different metasystem, a different role.
And here's the two metasystems, the traffic system and the fleet of buses. And we're only going to consider the pertinent metasystem, the fleet of buses.
So then how does system thinking help you find out why the bus won't start in the morning? Are we dazzling with our brilliance or baffling with our nonsense? What must we actually do?
Well, we understand the fleet of buses metasystem. And that means we call maintenance and we pass the problem to maintenance because that's what maintenance does.
So does maintenance actually use systems thinking to find out why the bus won't start in the morning?
Let's take a look. If they do, they address the fleet of buses meta system and they call themselves, which results in an infinite loop. So no, they don't use systems thinking.
Do you mean that we're going to use reductionism at this point? And if that's the case, then when do you use reductionism and when do you use systems thinking?
Well, first of all, let me tell you when we don't use them. We don't use them to create a solution to a problem. We use them to gain an understanding of the problem, and I'm using problem in its meaning of an undesirable situation. For example, to learn about something, to find the root cause of a symptom, to analyze a proposed conceptual solution to a problem. So let's go back to the problem of the bus not starting in the morning. So we have a problem. We need to find out why the bus isn't starting in the morning. So we take a look at it from a number of perspectives. Let's take a look at it from the operational perspective. When the driver turns the key, magic happens and out comes noise and vibration. The resources are consumed, petrol or gasoline in the US, oxygen out of the air, and oil. If magic doesn't happen, then we need to look inside the bus. So let's take a look at the pertinent subsystems or components of the bus that we need to examine. The battery, the engine, the starter, the switch, the transmission, and the wiring. And note, in order to identify these things, we need the domain knowledge. We can't do the analysis without understanding at least the parts of the bus. From a functional perspective, we have the battery, the switch, the starter, the engine, and the transmission. And the battery powers the starter through the switch. The starter starts the engine when the switch is turned, and the engine engages the transmission. That's our system of interest. So we do the analysis and we use the fishbone diagram to identify possible causes of identification. And we find out they could be the battery's discharge, the starter failed, the switch failed, the transmission locked. We did some troubleshooting and we found that the cause was the battery was discharged. We now move on to the next problem. Why is the battery discharged in the morning? And now we have a look at our pertinent subsystems. We now have new components. We understand the alternator, the battery, the engine, the lights, the starter. We're not concerned about the switch anymore, and we're not concerned about the transmission. And so from a functional perspective, we have these components. The alternator charges the battery. The lights discharge the battery whenever the lights are turned on. The battery powers the starter, which takes energy out of the battery when the engine is being started. So we have a different system of interest. We go through our analysis and figure out possible causes are the lights have been left on overnight, or there's a failure in the alternator and the battery isn't charging. We do some further investigation and we determine the actual cause. So far, so good.
Okay, so Joe, what about different types of problems? Like for a bus route, how frequently do I have to run the buses? Or how do we deal with boarding and alighting passengers? And what happens when we need to cross lanes to make a turn at an intersection? And how do we deal with the bus being blocked by other traffic or the bus needing to get through traffic during peak hours?
I'll answer that question, but before I do, let's just go back to that internal perspective of the bus, and you can see that these are the subsystems of the bus that we've already considered. And there are other ones that we know of, but have not been considered because we haven't dealt with problems in which they were involved. And so we'll draw a boundary about the entire bus and all the subsystems of the bus, irrespective of whether we've been interested in them before or not. we end up with what is termed a black box, in our case, a yellow egg. And now let's zoom out. We have the bus. Remember, the bus is part of metasystems, one metasystem and the second metasystem. And the type of problems you just asked about were problems that were outside the bus. The first set of problems dealt with problems that were inside the bus. We're now going to talk about problems that are outside the bus. So let's look at buses are running late at certain times of the day. So why are the buses running late at certain times of the day? Well, let's look at the subsystems of the traffic metasystem. They're buses, they're pedestrians, they're other buses, they're traffic lights, they're vehicles, vans, trucks, lorries, etc. And we can look at how these play together from the operational perspective. So let's now take a look at it from the functional perspective. Other buses are slowing down our bus. Other traffic slow down the bus. Passengers alighting and boarding slow down the bus. And traffic lights, whenever they come on, slow down the bus. Out of all the subsystems of the traffic subsystem, this is our system of interest. And so we use the functional view to identify possible causes, as I just pointed out. Passengers alighting and boarding, too many other buses, too many other vehicles. Some of the above, and even all of the above, are contributing to the undesirable situation.
So wait a minute, we just treated the internal and external problems in the same way. So what are the appropriate problems then that systems thinking and reductionism can address?
It depends. Which one to use to gain an understanding of the undesirable situation really depends on the nature of the problem. And actually, we did better. Did you notice that we changed the paradigm and dissolved the misconception completely?
No, what are you talking about?
Let me show you how. Consider the problem-solving process. This is the traditional view of the problem-solving process according to Derek Hitchens. It's define the problem, conceive solution options, identify ideal solution selection criteria for selecting one of the solution options, do the trade-off to find the optimum solution, select the preferred option, and then formulate strategies and plans to implement it. You then implement it, and then you verify that the solution system remedies the problem. And notice the feedback loop and the milestones, which are often milestone reviews. This is where we understand the problem in defining the problem space. And this is where we analyze solution options after they have been conceived. So these are the points in the problem-solving process where we are using systems thinking and reductionism. Let me share with you some of my slides from my class. Sherlock here is trying to understand an undesirable situation. He's inside the system of interest together with all the other parts, and he knows that there are blind spots because the triangle is hidden by the circle. Sherlock is pretty smart. What do you think he does to overcome the blind spots? Well, he moves. He goes to a different place in the system and looks from that perspective. And notice again, this time the circle is hiding the rectangle. And so he builds up a composite picture based on his understanding from different perspectives. He's also smart enough to know that you cannot understand a system solely from internal views. You must go outside the system. And then he looks at it from different perspectives. And notice how he's overcome the blind spots by viewing them from above. He's gone outside the system and he's looking at it from above. And he's also smart enough to know that he's got to turn around and look out of the system externally. And this is what Ackoff meant when he said, understand the role of the system in the containing system and understand the containing system. And even then, there are blind spots. So remember, Sherlock moves around and looks at it from different perspectives. And so the answer to your question, in summary, is if it's an internal problem, you identify the system of interest from the system viewpoint, which is the bus, and we extract the appropriate system of interest, which is a subset of the subsystems of the bus, as I showed you before. Understand the subsystem and the relationships between them to gain an understanding of the undesirable situation. If it's an external problem, we understand the appropriate containing system or metasystem, and we now have an internal problem when viewed from that metasystem. For example, it's a problem with a bus. Is it a problem with the traffic or the fleet or any other metasystem? We identify that metasystem, extract the appropriate system of interest, we understand the system of interest, and now it's an internal problem to that metasystem, and we deal with it exactly the same way as we dealt with an internal problem. An example of the systems approach is the bus won't start in the morning. Remember that? Well, let the bus be the system. And we now need an external view because we've got to fix the bus. And so the driver identifies the appropriate metasystem, which is the fleet of buses. The system of interest here is the bus and maintenance, because maintenance repairs buses. So the driver calls maintenance, exactly what he did before. And as far as maintenance is concerned, the bus is the system, and maintenance needs an internal view. So maintenance selects the appropriate system of interest from the subsystems in the bus, as described earlier. And so basically, we always identify the metasystem, and we view the system from the metasystem looking down. So in summary, misconception 1 is based on a misunderstanding of the words in isolation. Reductionism and systems thinking are analysis tools for understanding different types of situations. They're both tools for performing an analysis, and both can suffer from blind spots, and in isolation has a place in the process of gaining an understanding when we're building a model.
Okay, well, let's take a look at the second misconception.
Misconception 2, open and closed systems are different types of systems. Where did it come from? Well, it seems to have come from von Bertalanffy again. In the same paper, he wrote, "We call a system closed if no materials enter or leave it. It is open if there's inflow and outflow, and therefore change of the component materials." And Russ Ackoff pointed that out. He says, a closed system is one that has no environment, an open system is one that does. And then there's some other stuff I'm not quoting. And then he said, openness and closedness are simultaneously properties of systems and our conceptualizations of them. And the reality is, as we pointed out, open and closed systems are different perspectives or systems of interest of the same system. So so-called closed systems, like I showed here, are the system of interest when the problem is inside the system boundary. It's an internal view. So-called open systems, like I showed here, black boxes or yellow eggs, are the system of interest when the problem is outside the boundary. They're external views. And the problem bounds the system of interest. It's not me that's saying this. I'm quoting Churchman, Jackson and Keyes, and Beer, who wrote, "The boundary is crafted by the observer to enclose a section of the real world." And it's a long time since I looked at this, so I'm not sure if it's an exact quote. And here are the citations, if anybody wants to look it up for themselves. And let me give you an example of what I mean. Take a look at the solar system. The boundary defines the system interest as far out as Neptune. It's an internal view from the boundary, and it ignores the stars and any interstellar phenomena. If a sun nearby would go nova, we would definitely feel it in our solar system. So the solar system is considered as a closed system, or as an internal view, when we deal with understanding events that are happening inside the boundary of Neptune. A pendulum clock is also the other widely quoted example of a closed system. It's an internal view from that boundary. It ignores gravity and airflows. And if you would take your pendulum clock and put it on the moon or on Mars, you would have to change the weights because the gravity is different. So let's consider internal and external. And let's look at a bus. How it works is a closed system. It's an internal view from the boundary, and we look at it from the structure and functional views, and that's what you've seen before. How it behaves, on the other hand, it's an open system. It's an external view from the boundary. It's an operational view, and the system of interests are different in various scenarios in the different metasystems, just as I've showed before. Remember the bus internal perspective? System of interests depend on the problem that we're dealing with. And so the system of interest, when the bus doesn't start, looks like this.
But that looks a bit like a boot. Are you going to give it a kick?
Well, it depends on my emotional point at that time. First of all, I try to switch. Well, if I was in a hurry and I needed to leave somewhere, I might very well do that. On the other hand, if it's a problem of why the battery is discharged, here's our system of interest. And so each time we're bounding the system. Remember the bicycle? How it works? We look at the structural and functional views. It's a closed system. It's an internal view. How it's used, on the other hand, it's an operational view. It's an open system. It's an external view. And again, the system of interests will depend on whatever scenario the bike is being used for. How about a human being? How it behaves, open system, external view from the boundary, operational view, and again, the system of interests in various scenarios in different metasystems. Here's an example of a ballerina. An individual like you, me, or anybody in the audience is part of a large number of metasystems. The British Computer Society is one metasystem. Professional societies, families, clubs, nations, cities, counties, they're all metasystem of which we're parts. How it works, on the other hand, we use a different view. We use the closed system view. It's an internal view from the boundary. And again, it's structural views, like you can see here, and functional views. For example, cardiovascular system, the skeleton system, or the Chinese qi used in traditional Chinese medicine, the energy system. And the system of interest depends on the problem. For example, you can see here, we're dealing with the cardiovascular system. We then drill down and zoom into the heart. If we're looking at the lungs, we may drill down and look at the internal parts of the lungs. And then the other subsystems are shown here. The system of interest depends on the problem. So misconception 2, open and closed systems are different types of systems. It came about because people were always bounding the same system of interest and only dealing with one type of problems. The astronomers dealing with the solar system called it a closed system because that's the only type of problem they were dealing with. The observer bounds the system of interest to suit the problem, but we must always consider both the internal and the external perspectives when assessing a problem. Even if we find they're not pertinent, we start with an initial assessment. Which perspectives we use really depend on our level of expertise in dealing with that, whatever it is. And now, let's introduce the updated systems approach.
Systems approach seems to have been introduced by Wes Churchman in his book The Systems Approach that was first published in 1968 and has been reprinted a few times. Churchman was internationally known for his pioneering work in operations research, systems analysis, and ethics. In his book, he discussed the systems approach as a way to tackle increasingly complex problems. He introduced systems thinking as a part of the systems approach, but he didn't actually come up with a definition of the systems approach. The first definition of the systems approach I found was in the work of Simon Ramo, 14 years later. Simon Ramo created the following definition. The systems approach is a technique for the application of a scientific approach to complex problems. It concentrates on the analysis and design of the whole as distinct from the components of or the parts. It insists upon looking at a problem in its entirety, taking into account all the facets and all the variables, and relating the social to the technological aspects. The next mention of the systems approach, as far as I knew, was when Robert Halligan gave a talk to the Inkosi Singapore chapter in 2010. This is a picture of Robert at the time. Robert Halligan's definition of the systems approach was an approach to problem solving that views any problem as a part of a bigger system, and in developing a solution, sees that solution being achieved through the interaction of system elements such that the properties of the whole are beyond the properties of the individual parts. So Robert includes a definition of a system in his definition of a systems approach. 12 years later, I came up with the following definition of a systems approach. This definition sort of moves back to Simon Ramo's version. The systems approach is a technique for the application of a scientific approach to identifying and remedying problems. The systems approach, in a systemic and systematic manner, gains an understanding of an undesirable situation in its entirety, taking into account all the facets and all the variables by perceiving it from the appropriate meta-system depending on the nature of the problem, and plans and performs a transition from the undesirable situation to a feasible, desirable situation via one or more iterations. So the systems approach merges systems engineering and project management. And I will explain it more in detail in the future. So in conclusion, Misconception 1 is based on a misunderstanding of in isolation, reductionism, and systems thinking or analysis tools for understanding different types of situations. Both can suffer from blind spots. In isolation has a place in the process of gaining an understanding. Misconception 2 came about by people always bounding the same system of interest and only dealing with one type of problem. In reality, the observer bounds the system of interest to suit the problem. And once the system of interest has been bounded, it then falls into the typical classifications of systems such as man-made, natural, and we must always consider both the internal and external perspectives when assessing a problem. And the systems approach combines the best of reductionism and systems thinking. It builds on the GST to provide a methodology which minimizes blind spots and provides a universal, systemic, and systematic approach to identifying and remedying complex problems. Lessons learned. Don't assume a precept is true. Just because you heard it from somebody doesn't mean it's true. Remember the child's game of passing a message one child to the next, to the next, to the next, to the next. It's called Chinese whisper or telephone. And that's exactly what happens in the real world of adults. In order to overcome that, try to access the primary source and read the entire section of the source before citing it. Even better, read the entire article or skim it. If the primary source is unavailable, cite the secondary source, citing the primary source. And here's an example. This way, if the primary source was wrong,
you won't be wrong as well. You can just blame it on the primary source. And a research journey may not end up where you intended. First, we didn't intend to end up with an updated systems approach when we started this journey. We were just trying to understand why people said reductionism didn't work when history shows that it did. Thank you for staying with us. And now for the free gift I promised you at the start of the video. It's a copy of this book. It's a PDF version of this 585-page book on systems thinking and beyond, which is available from Amazon in Kindle and paperback hard copy. If you'd like the book, just send me an email stating that you've watched the video and request a copy. If you want to know more about the book, look it up on Amazon, or here's a QR code that will take you to the page on Amazon so you can look it up. Before we end, our thanks go to Ahmed Abadi, Raed Al-Qazi, Martin Yuji, Pascal Bahulu Mabello, Niels Malato, Shirley Seng, and Bo Wang, who made useful comments in the online Oasis Cafe and in my classes during the preparation of this session.